Welcome to section 3.1, polynomial functions. All right, let's start off with objective 1. Identify polynomial functions and their degree. So let's first define what a polynomial function is. So a polynomial function in one variable is a function of the form f of x equals a sub n x to the power n plus a sub n minus 1 times x to the power n minus 1 plus a sub 1x plus a sub 0, where all of your a's are constants called coefficients, of the polynomial. N is greater than or equal to 0, is an integer, and x is a variable. If a sub n does not equal 0, it is called the leading coefficient, and n is the degree of the polynomial. The domain of a polynomial function is the set of all real numbers. Okay? The monomials that make up a polynomial function are called its terms. Okay? So polynomials are the sum of monomials. If a sub 1 does not equal 0 and a sub n, if a sub n does not equal 0, a sub n x to the power n is called the leading term. A sub 0 is called the constant term. If all of the coefficients are 0, the polynomial is called the zero polynomial, which has no degree. Polynomial functions are usually written in standard form, beginning with the non-zero term of highest degree and continuing with terms in descending order according to degree. If a power of x is missing, it's because its coefficient is 0. Right? So we've defined a polynomial function and we listed some characteristics of polynomial functions. So now let's identify some polynomial functions. So now we're going to determine which of the following are polynomial functions. For those that are, state the degree. For those that are not, state why not. Write each polynomial function in standard form, and then identify the leading term and constant term. So for A, we have P of x equals 4x cubed minus 1/2 x squared minus 7. For it to be a polynomial, our coefficients need to all be constants. N is greater than or equal to 0, is an integer, and x is our variable, so it's only in one variable. So for P of x, we only have x as our variable, and n, which is our exponents, are all integers. All right. So this is a polynomial. So P of x is a polynomial. And since it's a polynomial, our direction tells us that we need to write each polynomial in standard form and then identify the leading term and the constant term. Okay. So this is written in standard form already because the powers are in descending order. They go 3, 2, and then 7 here has an x to the 0 power, which is 1. So they are already in descending order. So that means our leading term, which I'm just going to abbreviate LT, is going to be 4x cubed, and our constant term, which I'm going to abbreviate CT, is -7. Okay. All right. We also need to state the degree. All right. In reviewing our directions here. And so the degree of this polynomial is going to be a degree of 3. So that's our answer for A. Let's do B. F of x equals x plus 3 minus 5x to the 4th. Well, we have one variable. All of the powers are integers, and we have constants as our coefficients. So f of x is a polynomial. So the leading term is hard to find in this format because we notice here that our powers are not in descending order. So in standard form, f of x would be written as negative 5x to the 4th plus x plus 3. This now allows us to find the degree, find the leading term, and find the constant term. So this is going to have a degree of 4 because that is the highest power in our polynomial function. Our leading term is going to be negative 5x to the 4th, and our constant term is going to be 3. All right, C. G of x equals the cube root of x. Now, the cube root of x can also be written as x to the 1/3 as a power. All right, so that format might help you a little better in answering this question. Is g of x a polynomial? Well, we know one of the requirements for polynomial functions is that the power must be an integer. And so since our power here is 1/3, it is not considered, g of x is not considered a polynomial. So g of x is not a polynomial because okay, is not a, let's reorder that, it's not a, this is not a non-negative integer. Polynomial because does not have does not have a, gotta fix this grammar. Does not have, this does not have a non-negative integer. There we go. That makes sense. I want to make sure you have the correct verbiage in your notes. All right, so g of x is not a polynomial because the cube root of x does not have a non-negative integer. Okay. All right, let's do a couple more. H of x equals x cubed minus 2 divided by x to the 4th plus 1. All right. So here, h of x is not a polynomial because it is a ratio of two distinct polynomials. All right. So we have x cubed minus 2 in the numerator and x to the fourth plus 1 in the denominator, and both of those are considered polynomials. So this is a rational function where the numerator is a polynomial and the denominator is a polynomial. And therefore, h of x is not a polynomial. All right. E, g of x equals 9. Now, in looking at this, you might be thinking, oh, this isn't a polynomial, but it actually does meet the requirements of a polynomial. Remember, when you have just a constant, there is an imaginary x to the power 0 being multiplied by that 9. X to the 0 just means 1. That's what makes it the constant term. So we could state here that g of x is a polynomial with a degree of 0 whose leading term is 9, whose constant term is 9, and it is already written in standard form. That's pretty cool, huh? All right, our last one, capital H of x equals negative x cubed times the quantity x minus 3 squared. Well, to help us identify whether this is a polynomial function or not, let's factor out our function. So h of x is negative x cubed times x minus 3 times x minus 3. So let's multiply our two binomials together, and we will get x squared minus 6x plus 9, and then distribute our negative x cubed, which is negative x to the fifth, plus 6x to the fourth, minus 9x cubed. And now we have our function written in standard form. Okay? And in looking at this standard form, we see here that our powers are all integers, our coefficients are constants, and our standard form has our powers in descending order. So h of x is a polynomial. It has a degree of 5 because that's the highest power. Its leading term is negative x to the fifth power, and its constant term is 0. Okay? Although 0 is not there, it is always present. Alrighty. So, a summary of properties of graphs of polynomial functions. When you have a polynomial function of no degree, its form will be written as f of x equals 0. This is called the zero function, and on the graph, it would be the x-axis. Okay? When you have a degree of 0, this would be in the form of f of x equals a sub 0, where a sub 0 does not equal 0, because if it did, it would be the zero function. So when you have f of x equaling a value, this would be considered the constant function. And graphically, this would be a horizontal line with a y-intercept at a sub 0. When you have a degree of 1, all right, so now you have a term that has an x with a power of 1 plus your constant, where a sub 1 does not equal 0, because if it did, it would be the constant function. This would be considered a linear function. So this is a non-vertical, non-horizontal line with a slope of a sub 1 and a y-intercept of a sub 0. This is also the same format as the slope-intercept form. Now, if you have a degree of 2, all right, this would be considered a quadratic function. Okay? Graphically, it is called a parabola, where the graph is concave up if a sub 2 is greater than 0, and the graph is concave down if a sub 2 is less than 0. Okay? If you take a course in calculus, you will learn that the graph of every polynomial function is both smooth and continuous. A graph is smooth if it contains no sharp corners or cups. A graph is continuous if it has no gaps or holes and can be drawn without lifting your pencil from the paper. Looking back at A, we can start on the left-hand side and continuously go to the right-hand side. So that's what makes this example both a smooth and continuous polynomial function. Now, B, on the other hand, is the opposite of that. B is not a polynomial function because if you see here in this graph, we have holes. We have a gap in our graph where the two parts don't connect. We have a cusp and we have a corner. This is a great example showing you the different things that would make a graph not a representation of a polynomial function. So now we're going to dive in deeper into a specific type of polynomial function. So a power function of degree n is a monomial function in the form f of x equals ax to the power n, where a is a real number, a does not equal 0, and n is greater than 0 is an integer. For example, f of x equals 3x is a power function of degree 1. F of x equals negative 5x squared is a power function of degree 2. And f of x equals 8x cubed is a power function of degree 3. Depending on the value of a does not equal 0, the graph of y equals a times x to the power n will be a compression, a stretch, or a reflection about the x-axis of the graph of y equals x to the power n. Consequently, we next are going to explore graphing power functions of the form f of x equals x to the power n. To do this, we separate the graphs of f of x equals x to the power n into two cases. The first case is going to be when n is even, and the second case is going to be when n is odd. So let's look at power functions where n is a positive even integer. So the figure to the right here shows the function f of x equals x to the power n, where n is 2, 4, and 6. So that gets us x squared, x to the 4th, and x to the 6th power. In looking at all these graphs, we notice that all three graphs are symmetric with respect to the y-axis. Okay? This just means that the y-axis is like the mirror for both sides of our parabola. All three graphs contain the points 0, 0, 1, 1, and negative 1, 1. For each graph, the end behavior is the same on both sides. Okay? So that means both sides of the graph are either going to infinity and infinity. Okay, so they're both going to infinity in the same direction, whether x is going to infinity or negative infinity. Each graph touches the x-axis at the origin and steeply rises to the right and left of the graph. F of x is always greater than or equal to 0, and we know that because there are no values below the x-axis. As the power increases from 2 to 4 to 6, the portion of the graph around the origin, which is the minimum, becomes flattened. Okay? So that's this part right here, around the origin. As our exponents get larger, the bottom of the graph becomes more and more flattened. As the power increases from 2 to 4 to 6, the ends of the graph become steeper. For x less than -1 of x greater than 1. In other words, as x becomes unbounded in the negative direction, or as x becomes unbounded in the positive direction, the power function f of x equals x to the power n when n is even becomes unbounded in the positive direction. Okay, so it's going to go to infinity in the y direction when the power increases from 2 to 4 to 6, but it's getting closer and closer to the y-axis. So we define the behavior of the graph of a function for large values of x, either positive or negative, as its end behavior. Okay? So in conclusion, or I guess in summary, the properties of a power function where n is a positive even integer, f is an even function, so that means its graph is symmetric with respect to the y-axis. The domain is going to be the set of all real numbers, and the range is the set of non-negative real numbers, so all the positive y values. The graph will always contain 3 points, -1, 1, 0, 0, and 1, 1. As the exponent n increases in magnitude, the graph is steeper when x is less than -1 or x is greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. Okay? So our end behavior is saying here that as x is getting smaller and smaller, our y is going to infinity, meaning it's getting larger. And as x is getting larger and larger, our y is also getting larger and larger. All right. So that is the positive even integer for a power function. Now let's look at the odd integer of n for a power function. So the figure here to the right shows the function f of x where n equals 3, 5, and 7. Okay? So similarly, all three graphs contain 3 points. And these 3 points are 0, 0, -1, 1, and 1, 1. For each graph, the end behavior on the left and right sides are opposites. On the left side here, we are going to negative infinity. And on the right side here, we are going to infinity. So they're going in opposite directions. These functions are odd and have a range of all real numbers. As the power increases from 3 to 5 to 7, the portion of the graph around the origin becomes flattened. So that's similar to the positive even integer. As the power increases from 3 to 5 to 7, the ends of the graph become steeper. And this is for when x is less than -1 and x is greater than 1. Okay, so it's similar, some different characteristics, but similar concepts between the odd integer and even integer power functions. So in summary, the properties of a power function when n is a positive odd integer. So f then would be considered an odd function, so its graph is symmetric with respect to the origin. The domain and the range are the set of all real numbers. The graph always contains the points -1, -1, 0, 0, 1, 1. As the exponent n increases in magnitude, the graph is steeper when x is less than -1 or x is greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. For the n behavior, as x gets smaller, your f is going to also get smaller, meaning going towards -infinity. And as x gets larger, your y is also going to get larger, meaning going towards infinity. All right. So now let's look at some transformations when it comes to graphing polynomial functions. So we know some characteristics when we have an even integer and an odd integer. So now let's see if we can apply that to two transformations. So the methods of shifting, compression, stretching, and reflection studied previously, when used with the facts just presented, enable us to graph polynomial functions that are transformations of power functions. All right, so we're going to look at some examples where we're going to graph polynomial functions using transformations. So in this first example, we're asked to graph f of x equals 1 minus 7x. Okay, I'm going to write this in standard form just so that we can visually see this a little better. That's -7 or negative x to the power 7 plus 1. Okay, so this is an odd function. So I know it's going to take on the characteristics of a power function with an odd integer as its power. So I know it's going to have the points -1, 1, 0, 0, and 1, 1. Okay, and it's 7, which means it's going to be a little bit more flattened at the origin and then steep when we are greater than 1 and less than -1. So it's going to look something like this. Not perfect, but something of the sort. Okay. So now our next graph is y equals -x to the 7th. So the difference between these two graphs is that we are multiplying by -1. When you multiply by -1, you are reflecting over the x-axis. Okay, so if we're reflecting over the x-axis, our point 0, 0 is going to stay the same. Our point -1, 1, sorry, -1, -1, there we go. -1, -1, if I reflect it over, is now going to be -1, 1. And then my point 1, 1 is going to be now 1, -1. Okay. Now my graph looks something like this. There we go. That one's a little better. All right, and this is the origin. Okay. All right. So now I started with my power function, x to the 7th. We know that it's going to take on the form of an odd integer power function, odd integer power function. And then I multiplied it by a -1. which got me negative x to the power 7. And so now I'm going to add 1. And when I add 1, I shift the graph up by 1. Okay, so we're using transformations to graph f of x. So my point 0, 0 is now going to be 0, 1. My point negative 1, 1 is now going to be negative 1, 2. And my point 1, negative 1 is now 1, 0. Okay. And then we can do our graph here. Okay, and so now that is the graph of f of x. So we use transformations to help us get our graph. Let's do another one. F of x here equals 1/2 times the quantity x plus 1 to the power 6. So we're going to first start off with y equals x to the 6. This is an even power. So that means it's going to take the shape of a parabola. We know the parabola has 3 common points, 0, 0, negative 1, 1, and 1, 1. Okay. So next we are going to add 1 to our x variable. Okay, so we are going to replace x with x plus 1. So this means that we are going to shift left by 1. Okay? So if we're shifting left by 1, my original point 0, 0 is now negative 1, 0. My original point negative 1, 1 is now 2, negative 1. And my original point 1, 1 is now 0, 1. 2, and so let's draw a blah. All right. Okay. And then our next transformation to get to the function that we are asked to graph, f of x, we are going to multiply by 1/2. Okay? So if you multiply by 1/2, that means there's going to be a vertical compression by a factor of 1/2. Okay? So my original point, negative 1, 0, will remain negative 1, 0. That's not going to change. My original point, or I guess my previous original, not the original, but my previous point, negative 2, 1, is going to now be negative 2, 0.5. So that's going to be right here. Because I'm multiplying my y that I previously had by 1/2. So 1 divided or times 1/2 or divided by 2 is 0.5. And then 0, 1 is now going to be 0, 0.5. Okay. And this is my graph of f of x. Awesome. So that's using transformations to help you graph your function. knowing what your power is, you can start off with the standard form using those 3 identifiable points, and then apply the transformation step by step to get your function. Awesome.